Our next speaker is Hiraku.
I think I have plenty of time. So I'm going to talk about the constant run private decision tree evaluation for by using secret sharing data. This is a joint work with Nan and Katerina from University of St. Gallen and Naman from IIT Delhi and Kazunari from the University of Tokyo, and me from Aarhus University and the University of Copenhagen. Let me start with showing the example of the setting of our work. Users on the left and the service provider is on the right. Let's say this service provider wants to provide, for example, healthcare analysis service. And then as a user, you send your personal information to the server or the service provider. And then you will get your analyzed data, for example, if you're healthy or not. In this setting, you have to send your sensitive information, for example, your DNA data or your biometric. Once such kind of personal data is leaked, it's not only your own problem, but sometimes if the DNA data is leaked, it's also your problem for your family. So you do not want to send such kind of sensitive data in plain text form. Also, the service provider doesn't want to store the sensitive data from the individual. So using multi-party computation, you can somehow solve such kind of problems. I wrote 3 servers in the middle. These are often called computing parties or computing servers. They compute the exact same computation, but using multi-party computation. So in this setting, user encrypt their data and send it to these 3 servers. And then 3 servers somehow compute with using these encrypted messages. And in this setting, the users don't have to send the personal information in plain text form, as well as the service provider doesn't have to store the individual personal data. Then the secure computation we consider is the private decision tree evaluation. So most of the work, not most of, some work consider secure comparison, some work consider secure division, so on and so forth. But in this protocol, we use secure comparison and some other protocols and combine together and then do the decision tree evaluation. Okay, before going into the technical part, I'd like to share the comparison table. In previous work, most of them required linear round complexity for the computation of PDT. Most recent work by Tsuchida et al. In 2021 constructed a private decision tree evaluation using secret shared data within a constant run, which is 25 rounds. But we thought this 25 rounds was still large when you're using a network with a big delay. So this is a starting point. We want to improve the results. Okay, let's get into the private decision tree evaluation. I have a decision tree evaluation, textbook style of decision tree evaluation here. In our work, decision tree consists of, a decision tree is a full binary tree. That consists of, each node has the following information, index of attributes, and conditional flag to choose an operand. So you can choose less than protocol or equality protocol. And the nodes also store a threshold value. So let me give you a concrete example. So let's think that this service is determine your nationality. So you have input X. So for example, this is my input. I have features or attributes that describes myself. So my height, my weight, the language I speak, so on and so forth. There are a lot of features you have. So you put the input to the service. So in this slide, I show non-MPC style, so just a plain text form decision tree evaluation. The algorithm starts from the root node. So this root nodes, for example, let's say have a index of attributes 1. Then you think of attribute 1, which is weight. And this root node has a threshold. So you compare with your weight with this threshold. Then if the comparison result is 1, you go down to the right. And if the comparison result is 0, you go down to the left. So on and so forth. You do the same thing to the next layer. You pick the index of attributes here. Then if it's the height, you compare with the height with some numbers. Then you do the same thing until you reach to the leaf node. And then finally you can get the information that I am Japanese. This was done in the plain text form, so non-secret shared form. But you have to do this in secret shared form. All the information are stored in the secret shared form. So you cannot see the data itself, but it's a secret shared or encrypted. So also the input features are also secret shared. So you cannot see my height, weight, and language I speak. So we constructed these 3 sub-protocols to construct a private decision tree evaluation. One is attribute selection, and second one is secure comparison protocol, and the last one, path evaluation. In this talk, I only focus on presenting path evaluation. But attribute selection and secure comparison protocols are also interesting. We use one-hot vector technique, which can be also applied to constructing lookup table protocol. And also secure comparison, we use function secret sharing for that, but we combine a very nice share conversion protocol with a comparison protocol to make everything efficient. Okay, let's go to the path evaluation. Let's play with path evaluation in non-MPC setting. So let's assume that you already computed the secure comparisons. So all the nodes already have the results of the comparisons. So it's a 0, 1. So the algorithm starts from the root node. If it's 0, you go on the left. And if it's 1, you go to the right, and so on and so forth. Then finally you can get to the final leaf node, and then you get the final result, V3. Because in this slide, please remember we reached to the value V3. I will use it later. All right, so in this non-MPC setting, you didn't even care about other nodes, right? You just see the root node, and then if it's 0, you go to the left, and so on and so forth. You only see the nodes on the path. But in MPC setting, you cannot see anything. All the information is stored in secret shared form. We used a secure tree shuffle protocol using a secure shuffle protocol that's already well studied. High level idea is like this. You have hidden decision tree or secret shared decision tree. You somehow transform it to visible decision tree. So you randomize the tree, and then you reveal it. Now you can see it. Okay, let's see that from the top nodes, you see 1, so you go to the right, and then you see 0, you go to the left, so on and so forth. Finally, you reach to the final result V3, which is exactly the same as before. How we did do that? Let's just highlight. Let me just highlight this permutation. Preserve the relations between parents node and child nodes. So let me show real quick how we do it. Let's assume that we have this aging tree here in the middle. We can pre-compute this, so we can prepare this before protocol starts. And then this is the left-hand side. This is the original tree I showed. And then you see 1 here. Then you flip the child node, the sub-trees. So child's node with connecting with red edge and blue edge swapped, like this. And also you can see 1 here, and 1 here. Then you swap the yellow edge and green edge, swap. Then after that, you add this aging tree to the tree. Then it's the tree is randomized, so you can reveal it, and you can get randomized tree. Then you don't need to care about secret shared form. You just see the plain text decision tree. Okay, this is our result. You can see that if the tree is small, like a depth of 5, depth of 7, it's reasonable. We use 3 servers in the world, in San Francisco, Frankfurt, and Singapore. Then to send a message, it takes around 160 millisecond or 180 millisecond. So if you use our 5-round protocol, it takes 800 millisecond for only communication. So you can see that if the tree is small, like 7, all the execution time is coming from the communication time. And this is sad, but if we consider a tree depth with 15, it takes more time. But we say in the paper, oh, it's still reasonable. Thank you very much.
Okay, we have time for a few questions. All right.
Thanks for the nice presentation. Are you familiar with the systems or designs, for example, Sorting Hat or Level Up? The one came in CCS 22, another came in CCS 23. They are based on homomorphic encryption techniques. They work with one single untrusted server. And for similar tree depth, for example, tree depth 7, they will probably take less than 100 milliseconds. So how do you differentiate your system from those systems, or what are the advantages of using these systems over that system?
Is it a 2-party setting?
It's a one single untrusted server and the client. There are no 2 servers, and that is untrusted.
Okay, so computation is only done in this untrusted server, and then
Yes.
It's encrypted in homomorphic encryption.
Yes.
That's a good question. So it's a comparison with the construction in homomorphic encryption and construction in secret sharing form like ours. The good point in construction in secret sharing scheme is you only need to care about communication rounds complexity. So you don't interactive. Yeah, I know. I'm explaining the secret sharing scheme. So we only focus on reducing the rounds. That's how we do it. Then in homomorphic encryption scheme, I suppose the computation is quite large compared to a secret sharing scheme. And also, you have to use oblivious transfer or some other public key crypto systems. So we consider it quite heavy compared to a secret sharing scheme.
The total computation time is less than 100 milliseconds.
Oh, okay. Thank you for the pointer. I will check.
Thanks for the nice presentation.
Thanks.
Okay, I think we have time for one more question for this speaker, and then apparently our last speaker is now on Zoom, so we could take maybe one or two questions for them.
Hi,
Hi.
thanks for the presentation. My question is how you find the position of a particular person in a tree, like what you do to estimate that you have to place this particular person at this place. And another thing is you are using the attributes like height, weight, and maybe there was one more attribute, but there can be some overlapping because there may be so many people in a country with that particular height, that particular weight. So how you distinguish like that? So, yeah.
If I'm small and speak Japanese, I'm Japanese. Is that your question?
It's about the uniqueness of the attributes, how you distinguish between users, because there will be attributes that are overlapping.
Actually, it's out of scope. It's a machine learning problem. So we use the learned model. So this model is already learned. So how you distinguish is learned already.
Okay.
So we didn't touch it. So how to distinguish people or how to distinguish these input features, it's out of scope. But it's already learned. So we only use the learned model on SQL Share. Thank you for the question.
All right, thanks, Haraku.